Welcome back to 6.3, where we're dealing with the trends on the periodic table, which we call periodic trends. And the first trend that we took a look at was atomic radius. And the trends in atomic radius, though they are counterintuitive, make sense when you're dealing with the strength of the nucleus and where the electrons are located. As you go from left to right, the atoms actually get smaller because the nuclei get stronger. The electrons are not being added to a different energy level. They're all in the same energy level, so they're not any further away from the nucleus. But because that nucleus gets stronger, it draws the electrons closer and shrinks the size of the atom. As you go down the periodic table, the reason why they get bigger is not because you're adding more stuff. Again, most of the atom is empty space. The reason why they get bigger is because the electrons are being added to further or outer energy levels further away from the nucleus, and that automatically makes them bigger. The next trend that we're going to look at deals with ionization energy. Now, first of all, what are ions? We're talking about ionization. Well, what is an ion? An ion is any charged particle. Okay, we're kind of crossed over here just a little bit, so we'll draw an arrow down. This is an atom that has lost or gained electrons, either way. Now, if the atom has lost electrons, we call them cations. If they have lost electrons, they are positively charged. Why? Well, let's take a look at something like sodium. Okay, sodium normally has 11 protons, or it always has 11 protons. And it also has 11 electrons when it's neutral. However, if it loses one electron, so we're going to take an electron away, what's going to happen is that sodium, which still has 11 protons, is now down to 10 electrons. Well, these 11 protons and these 11 electrons originally cancel one another out. You have 11 positives, 11 negatives, so it's overall neutral. However, here in the product side, only 10 of these 11 protons are balanced by electrons. You only have 10 electrons, so only 10 protons are balanced. You have one proton that is not balanced by a negative charge, so it overall has a +1 charge. All right, this is called a cation, and we're going to be using cations quite a bit when we start creating compounds. On the other hand, you have what are called anions. Anions are the opposite. They have gained electrons. All right. If they take on electrons, they will be negatively charged. And the example we want to use here is chlorine. Chlorine has 17 protons, and therefore it has 17 electrons when it's neutral. However, if it gains an electron, now where's it going to gain an electron from? Well, it could gain it from sodium that's losing it. But when it gains that electron, the chlorine, which has still 17 protons, now has 18 electrons. Now you have the opposite effect as the sodium. You have 17 protons that will balance 17 of the 18 electrons, but that leaves one electron that is unbalanced. So therefore, that one electron's negative charge remains unbalanced, and so the chlorine atom now has an overall negative charge. All right? So atoms can lose and gain electrons to form ions, cations and anions. Now, in order to remove electrons from an atom, you have to give it some energy. It takes energy to strip that electron off. And so we're going to take a look at the trends in the amount of energy it takes to remove an electron. That is what is called ionization energy. Ionization energy, again, is the energy required to remove an electron from an atom. All right? Now, scrolling down here. We have different ionization energies. You have what is called the first ionization energy, the second, the third, and in fact you could go on, 4th, 5th, 6th, 7th, 8th, whatever. The ionization energy is referred to the amount of energy it takes to remove a particular electron. The first ionization energy is the energy required to remove the first electron from an atom. If you want to remove a second electron from an atom, you have to add more energy. That is called the second ionization energy. If you want to remove a third electron from an atom, that requires more energy, called the third ionization energy. Every electron requires a certain amount of energy, and so we simply name the ionization energy after the number of electron that is being removed. All right? So what's going to happen here? Let's take a look at something like nitrogen. Okay, how much energy does it take to remove an electron from nitrogen? Well, first of all, let's just say you have nitrogen here, which has 7 protons and 7 electrons. 1, 2, 3, 4, 5, 6, and 7. Of course, they can occupy different regions here. We're not talking about orbitals right now. We're just talking about sheer numbers. All right. It's going to take a certain amount of energy to remove one of the electrons, to pluck it off. Okay. Why? Because this electron, negatively charged, is going to be attracted to this nucleus, which is positively charged. But now what happens is, if you remove this electron away, so this thing is gone, when you remove that, there's less repulsion among the other electrons. So they can space themselves out a little bit better. And I'm going to go ahead and draw that in blue here. They can space themselves out a little bit more. Because there's less repulsion going on, the nucleus can draw them in tighter. Now, the nucleus can only draw them in so tight before they start repelling each other again. But because you have one less electron to account for, the nucleus can draw them in tighter, less repelling going on. Now, the next time you remove an electron, so by the way, that first ionization energy, I'm going to go back to red here just so it's consistent, would have taken 1,400 kilojoules of energy. To remove the second electron now, notice that it takes almost double the amount of energy, actually more than double the amount of energy. Why? Because the electrons are now tighter to the nucleus. And the closer and tighter they are to the nucleus, the harder they are to pull off. So we're going to go ahead and pull off another electron. Okay, that gets drawn off, but it takes a lot more energy. Now you're down to 5 electrons. Let's go ahead and put these things in green. Because you have 5 electrons, there's more space between them. They can space themselves out a little bit better, but then the nucleus is going to draw them in even tighter because there's less repelling going on amongst the electrons. But because the electrons are now even tighter to the nucleus, it's even harder to remove them. And so the third ionization energy is much higher yet. So each successive electron is always harder and harder to remove. The reason why, again, is because the electrons are getting closer and closer and closer to the nucleus. And when they get closer and closer and closer to the nucleus, they get harder and harder and harder to remove. Also, what's really interesting to look at is the amount of energy that jumps up when you start a new row. For example, sodium. I'm going to go back to red here. Sodium, the first electron only takes about 500 kilojoules of energy to remove. However, the next electron takes about 9 times that, between 9 and 10 times the amount of energy. It's an incredible jump. Why is that? All right. Well, if you take a look at sodium, sodium's electron configuration, it has a couple of electrons in the first energy level. It's got 8 electrons in the second energy level, and then it only has 1 electron in that third energy level. So it's got 2 electrons here. It's got 8 here. 1, 2, 3, 4, 5, 6, 7, 8. And then it only has 1 electron in this outermost energy level. This electron right here is relatively easy to remove because it's so far from the nucleus. But now once that goes away, first of all, the rest of the electrons get pulled a little bit tighter to the nucleus. So this whole thing shrinks up a little bit. Okay? So instead of the size of the electron being way out here, the size of the atom being way out there, going into blue here, now the size of the atom is going to be more like this. It's going to be the second energy level, but it's going to even be drawn in tighter. So there's a big, big difference between the size of the sodium atom and the sodium cation. The other reason why that this energy level is, the amount of energy to remove the second electron from sodium is so large, is that now you're trying to remove an electron from an inner energy level, and that is incredibly difficult. It is very, very tight to the nucleus. I'm not saying you can't remove it, but it is incredibly difficult. Lots of energy is required for that thing to happen. All right? So in terms of ionization energy, the first thing that you should know is that it takes an incredible amount of energy. First of all, it takes more energy to remove one electron as it did the previous electron. It gets progressively harder to remove electrons. It's incredibly true when you're dealing with electrons from inner energy levels. Outer energy levels are relatively easy to pull off, but as soon as you get to an electron from an inner energy level, they're very, very difficult to remove. All right. In the next podcast, we're going to take a look at the periodic trends when we're dealing with ionization energy.